Hello, everyone. Welcome to our podcast, where today we'll be diving deep into the paper Kling-Avatar, grounding multimodal instructions for cascaded long-duration avatar animation synthesis. Are you ready to explore the next generation of avatar animation synthesis?
Absolutely. This paper introduces Kling-Avatar, a novel framework that unifies multimodal instruction understanding with photorealistic portrait generation. It's a big leap forward in digital human animation. Shall we start with the motivation behind this work?
Yes, let's do that. The authors point out that recent advances in audio-driven avatar video generation have improved audio-visual realism, but existing methods mostly treat instruction conditioning as low-level tracking. They don't really model the communicative purpose behind the instructions. Why is this a problem?
That's a great question. Without modeling the communicative intent, the generated avatars may lack narrative coherence and expressiveness. For example, an avatar might sing a sad song while smiling, which is visually polished but semantically inconsistent. Kling-Avatar aims to bridge this gap by understanding and grounding multimodal instructions.
Exactly. The core idea is to move from shallow, modality-specific cues to a unified, semantic understanding of instructions. Kling-Avatar achieves this through a two-stage pipeline. Can you explain how this pipeline works?
Sure. In the first stage, they use a multimodal large language model, or MLLM Director, to interpret multimodal instructions like audio, images, and text prompts into a high-level semantic plan or storyline. This blueprint video encodes character motion, emotions, and scene layout. In the second stage, guided by keyframes from the blueprint, the system generates multiple subclips in parallel, refining local details and dynamics.
That's right. This cascaded, global-to-local framework preserves fine-grained details while ensuring the generated video aligns with the high-level intent. It also enables fast and stable generation of long-duration videos, which is crucial for real-world applications like digital human live streaming and vlogging.
Speaking of real-world applications, the authors constructed a benchmark of 375 curated samples covering diverse instructions and challenging scenarios. This benchmark is used to comprehensively evaluate Kling-Avatar's performance. What are some of the key metrics they used?
The main evaluation metric is the good same bad, or GSB, protocol, which is based on human preference. For each sample, 3 participants compare Kling-Avatar's output with baseline methods and rate them as good, same, or bad. The final label is determined by majority vote. They also assess specific dimensions like lip synchronization, visual quality, control response, and identity consistency.
That's a thorough evaluation. The results show that Kling-Avatar outperforms state-of-the-art baselines like OmniHuman 1 and HeyGen across most dimensions, especially in lip synchronization and visual quality. It also generalizes well to open scenarios, including anime, cartoons, and stylized characters.
Let's talk about the MLLM Director in more detail. How does it ground multimodal instructions into a unified global plan?
The MLLM Director uses models like Qwen 2.5-Omni and Qwen 2.5-VL to extract transcriptions and emotions from audio and generate descriptions from images. These are combined with user prompts and processed to output a coherent storyline. The storyline template is specified using in-context learning, prioritizing user knowledge, audio, and image references.
The storyline includes key elements such as character features, background layout, actions, visual style, camera planning, and emotional shifts. This unified textual prompt is then injected into the video diffusion model through a text cross-attention layer to generate the blueprint video.
In the second stage, the blueprint video is segmented into subclips. High-quality anchor frames are selected around segmentation points, ensuring identity consistency and expressive facial details. These serve as first-last frame conditions for generating adjacent subclips in parallel.
That's a clever approach. By generating subclips independently and in parallel, the system can produce arbitrarily long videos with nearly the same runtime as a single clip. This is a significant advantage for long-duration video synthesis.
To ensure precise frame synchronization with input audio, they use an audio-conditioned interpolation strategy for transition frames. This avoids misalignment between anchor frames and speech timing, resulting in seamless and temporally coherent transitions.
Now let's discuss the data preparation process. The authors emphasize that data quality is more important than data scale. They collect thousands of hours of audio-visual content from various sources and use expert models for rigorous filtering. What are some of these filtering techniques?
They use lip clarity filtering, where a binary discriminator classifies lip region clarity to filter out videos with ambiguous or motion-blurred lip movements. Temporal continuity detection is performed using a temporal coherence discriminator and pi-scene detect to remove discontinuous clips. Audio-visual synchronization is assessed with SyncNet, and aesthetic quality is evaluated using video aesthetic scoring methods.
After filtering, they manually curate the retained samples, assembling hundreds of hours of high-quality human portrait videos for training. The benchmark dataset includes images from real videos and AI-generated content, audio tracks in multiple languages, and text prompts with explicit specifications on emotions, actions, and camera movements.
This comprehensive benchmark establishes a demanding testbed for evaluating vivid and coherent portrait generation under complex multimodal instruction control. It's impressive how much effort went into data curation.
Let's move on to the training and inference strategies. To strengthen the alignment between lip movements and speech, they inject audio features into the audio cross-attention layer using a sliding window scheme. They also assign higher diffusion denoising loss weights to the mouth region using DW pose.
Additionally, they randomly pad empty pixels around video frames during training to encourage robustness under small face and long shot conditions. The parameters of the text cross-attention layer are frozen to preserve text controllability and prevent overfitting.
During inference, the first-last frame conditioned parallel generation framework helps alleviate identity drift, a common problem in long video continuation. They introduce a negative frame, classifier-free guidance mechanism, using degraded reference images as negative signals to guide the denoising process toward identity-consistent directions.
Since ground truth frames for mouth region masking aren't available during inference, they increase the audio cross-attention values to strengthen lip audio alignment. These strategies collectively improve lip synchronization accuracy and visual audio alignment.
Now let's look at the experimental results. Kling-Avatar consistently outperforms OmniHuman 1 and HeyGen across all dimensions in the GSB evaluation. Notably, HeyGen's approach of looping a 5-second action pattern enhances motion stability but harms vividness and diversity.
Kling-Avatar supports arbitrary input and output resolutions, producing videos up to 1080p at 48 FPS. It's also more extensible and adaptable to broader applications, as it's built on a general video generation foundation model.
The visual comparisons show that Kling-Avatar produces accurate lip movements for various syllables, while baseline methods struggle with alignment and sometimes fail to respond. The generated videos exhibit vivid emotions, rich actions, and precise lip synchronization.
The system also demonstrates strong generalization to diverse scenarios, including multi-person, cartoon, anime, and non-human characters. The long-duration video synthesis results show stable identity preservation, coherent visual quality, and rich character dynamics.
Let's briefly touch on related work. The paper discusses the evolution of video generation, from early UNet-based approaches to the current mainstream of diffusion transformers. These models compress videos into spatiotemporal tokens and leverage transformers' large context capacity for stable, large-scale video generation.
In audio-driven digital human synthesis, earlier methods used explicit intermediate representations like facial landmarks or 3D head models, but these were limited to facial animation. Recent diffusion-based methods achieve joint alignment and control of audio, expressions, and motion, enabling realistic and coherent video synthesis.
However, existing methods still rely on local cues for alignment within each modality and struggle with multimodal instruction understanding and consistent long-duration generation. Kling-Avatar addresses these challenges by using MLLMs for instruction grounding and a cascaded framework for fast, vivid, long-duration portrait animation synthesis.
In conclusion, Kling-Avatar represents a significant step forward in digital human animation. Its two-stage pipeline, guided by an MLLM Director, enables the generation of lifelike, expressive, and long-duration avatar videos that faithfully follow multimodal instructions.
The carefully curated data, practical training and inference strategies, and comprehensive benchmark evaluation all contribute to its superior performance. Kling-Avatar sets a new benchmark for controllable, high-fidelity digital portrait animation synthesis.
This work opens up exciting possibilities for real-world applications in virtual assistants, education, media content creation, and immersive telepresence. It also lays the groundwork for future research in instruction-grounded, long-duration avatar video generation.
That wraps up our deep dive into the Kling-Avatar paper. To summarize, Kling-Avatar introduces a cascaded framework that unifies multimodal instruction understanding with long-duration, high-fidelity avatar animation synthesis, achieving state-of-the-art performance across multiple dimensions and setting a new standard for digital human video generation.
Thank you for joining us today. We hope you enjoyed this detailed review. Stay tuned for more in-depth discussions on the latest research papers in AI and computer vision.
Goodbye, everyone.
Goodbye.